good. Welcome to the HKS Energy Policy Seminar. I'm Joe Aldi, and I'll serve as the host for today's talk. As usual, this semester, we are holding this in hybrid format. Pleased to have our friends, alumni, colleagues, and staff joining us online. And pleased to have a full room with us here today for today's seminar. We're pleased to welcome Vijay Swarup today for his talk, ExxonMobil's Approach to the Energy Transition. Dr. Swarup is the Senior Director for Climate Strategy and Technology for the ExxonMobil Corporation. Vijay currently oversees the corporation's strategy to reduce greenhouse gas emissions and address climate change. This includes climate policy and advocacy initiatives, along with the interplay between policy and the advancement and implementation of technology. For nearly a decade, he headed the research and development team, overseeing a research portfolio that focused on groundbreaking initiatives in biofuels, carbon capture, direct air capture, and hydrogen. He's served at ExxonMobil for more than 30 years and held a variety of leadership roles in both business and technology functions. Vijay, welcome to the Energy Policy Seminar.
Thank you so much for the key is you clap at the end. But thank you so much for giving me your time. And would you have come if there wasn't free lunch? That's a really important question here, right? I do these at various places, and like, was this mandatory attendance? And they all say yes, and I was like, well, that's not as exciting. I do really appreciate you taking time out to have a really important discussion around where are we in this journey. There's a lot of noise out there, a lot of talk out there, and we're going to actually try to reduce it to practice, reduce it to action, and use real world examples of what is actually going on. Sort of three parts to this talk. First, what is energy? Why does it matter? How do you actually use it? Second is, where are we on this transition? And the third is, let's get to solutions. As an engineer, I like to solve problems. So I want to get on to what are we actually doing to meet the world's energy needs and reduce emissions. So we could spend the entire seminar on this cautionary statement, but I'm going to skip over it, but it's a necessary thing to do. And we're just going to talk about me for just a second, just to introduce myself. And thank you for that really nice introduction. Once you hit 30, you stop counting. But if you want to know the count, it's actually 38, a little over 38 years that I've been with the company, which is longer than most of you have been with the planet. So I've been around for a long time, and I've had the luxury of having a lot of jobs, running business units, leading R&D, and the last couple of years really diving into this topic around climate science and climate technology and how does this all come together. And really in this role, getting to work with folks like yourselves, leading universities around the world, the startup community, as well as a large corporation like ours that manages huge amounts of capital and does things at scales that are really unimaginable. So enough about me, because I could spend the whole time talking about me. But what I really want to do is just remind everyone, so what is energy? Because not too long ago, on the left is how things were done. And actually, I could even go further left and say how things were done 100 years before then. And these pictures on the left, y'all are looking at it and saying, wow, that's hard to believe, because we're living in the right. We're living on the right side. We're living in the world of AI. We're living in the world of medicine and iPhones. And I mean, I'm old enough. When I joined the company, we didn't even have answering machines. I got an answering machine, like a tape answering machine. You guys remember those? You guys don't even know what that means. My tangents have tangents, I'll warn you, but I will tell you just a quick thing. It's worth doing. I had a long overseas flight and was able to watch the Mission Impossible series, which scans 1996 to today, which, I started in 87, so it doesn't even, but the original, if you go back and watch Mission Impossible 1, it's held on a 3¼ inch disc. That's actually what Tom Cruise is going in there to steel. And then you look at today, it's 5D plasma is what the entity resides in, right? I mean, it's amazing how the technology has evolved. And that's what you see on the right, that a cell phone, and today it's AI, and the thing on the lower right is quantum computing. And so the fascinating thing about technology and the fascinating thing about man is we're never done. That's why I loved research and still love research, because you're never done. There's one more step. There's one more improvement. This concept of infinity has always inspired me. And so the right is going to keep moving to the right. And that's a really, really good thing. The problem is there's a whole lot of people still on the left. There's a whole lot of people that still think this is how things are done. And we got to move the people on the left to the right, and the right needs to keep moving to the right. And that's the energy problem. Okay? To do that, you need to have lots and lots of energy, because we know this. So the physics definition of energy is the ability to do work. Right? So if you guys all took physics, and it's that simple. And so the more work you do, the more energy you need. It's actually that simple. And so it's not surprisingly that you see a correlation between GDP, population, all those things tied to energy. So from 2000 to today and then onward, you can see that population goes up, GDP goes up, energy consumption goes up. And not surprisingly, if you look at the difference between the OECD and the non-OECD, we were talking about it earlier today. It's sort of a limit function. Like at some point you level off, and that's what you see in the OECD. And it goes from I just need basic needs to now I need efficiency gains. So, it's a limit of t from t goes to infinity, and you'll see the leveling off. The thing is that the developing nations haven't really kicked into the curve yet. And I'll show you some charts there in a minute. But that's it. You got to bring these three things together: population rise, GDP rise, per capita income rise. And they all underpinned by energy. The absence of energy, you can't do this. And here's just another view of the same thing, which now puts it into context as to how much is still on that left side of that picture I showed you earlier. Because where we drew the cutoff for energy is really minimal requirements of energy. It is not what we're enjoying here today. The luxury to have enough air conditioning in a building that you actually have to wear a sweater. Okay? The luxury to have enough heat in a room that you actually have to take your sweater off because you have so much heat, right? There's a whole bunch of people that just want propane to cook on. They just want a washing machine. They want a light bulb. They want, whenever, I don't like that term abject poverty, because I don't want to eliminate poverty, not abject poverty. So, and that's just 50 million BTUs per person. And you can see how much of the world is to the left of that. So one of the nice things about being an engineer is engineers always like to reduce things to problems. And in fact, the first thing you learn in engineering school is how do you define a problem? So you get a problem, you read the problem, you reread the problem, you draw a picture of the problem, then you write the problem down, and then you write the assumptions. You use like 5 steps before you even try to solve the problem. So a really important theme of this discussion is what's the problem? Because if we can get the problem right, we're going to get the answer right. If we don't get the problem right, it gets really hard to get the right answer. And the problem is actually a very simple problem. It's the first part of the problem is the world needs more energy. Now, again, go back to when I started, the world didn't have enough energy. So to close this gap wasn't even a thing. It wasn't going to happen. But because of technology, we actually have enough energy to go around the world. Now, it may not be in the right place at the right time, but the macro balance says you have enough energy. Why is that? Because we have geothermal, because we have solar, because we have wind, because we have nuclear, because we have fracking, because we have all those other things that allow us to have the energy. But as things happen, one problem solved, another problem opens. And so now we have this additional challenge of we need more energy and we need to reduce emissions. That's the challenge now. So not just energy, It's energy with lower emissions. And now we're back to the research. Now we're back to, okay, we got to solve this problem. But now we know what the problem is. And so lots of people study it. You guys may or may, I'll try to go through the alphabet soup with you a little bit. So the IEA is the International Energy Agency out of Paris. They put out different scenarios. So the steps is basically the stated policies. It's where we are today. The APS is the announced policy. So it's what we say we're going to do. So one is up to now, one is going to the future. And I think I'll show you on the next chart what they call net zero. There's some more alphabet soup coming. But the point is we've been rising emissions. You can see the pandemic dip that we don't want to go back to, and then the rebound as we came out and started to do things again. And so while we look like we're bending the curve, we're not on the track of less than 2 degrees, let alone net zero. And while progress is being made, as you can see on the right, and again, this is a very, very complicated problem. It's not just more energy. It's more energy for buildings, for lights, for cars, for transportation. Has 4 dimensions of transportation. This is a massive, massive problem. And you can see that this is energy-related emissions, about 37 gigatons. Total emissions, about 57. I think the data I saw over the weekend says we're now at 423 parts per million. And so emissions continue to rise. And while we see a reduction, we still don't see the pathway to actually get to where we want to try to get to, what we aspire to get to by 2050. And so we're going to talk about how do you close that gap in just a minute. But before I do that, I want to just again now talk about one of the things that people always want to know is, do we need more oil and gas? Do we need more energy? Well, the first concept in energy you have to remember, and energy is kind of pretty simple to think about it. What is the value chain of energy? You find it, but you just find an energy source. You really don't want the energy source. What you want is the energy carrier. So the first thing is you got to do, find it. Then you got to convert it, and then you've got to use it. And as soon as you use it, what do you have to do? You have to go find it again. So everything we do in energy, by the way, that's true for sun, that's true for wind, that's true for anything. Until we get, I know just down the road somewhere here is Commonwealth Fusion. Until we get to fusion, everything we do is going to be depletion. It's just how big is your source for depletion, right? Solar obviously is replenishable, but it's still, once you've taken that solar ray and turned it into an electron, you got to go find another solar beam. Okay? So what this chart really shows, and I'm just going to start with the alphabet soup here. So when we say global outlook, that is what Exxon publishes. If you go up to the ExxonMobil website, you will see various reports. One of them is the global outlook. That is a team of economists that really looks at all these things and builds from the bottom up where we think energy is and where we think the trajectory is for energy is going. And now we get into the alphabet soup. So IEA, we already talked about steps we talked about. That's the trajectory we're on today. So that's sort of business as usual. The IPCC case is now likely below 2-degree average. Announced is the announced pledges. So that's taken all of the NDCs, taken all of the policies that are in the works and saying, okay, if we model these things, that's the trajectory we're on. And then net zero. And what these are against is how much oil do you need? And so the first thing you realize is even in the net zero scenario, you still need oil. Right? You still need a CH bond. And the most thermodynamically efficient way to get a carbon-hydrogen bond is either oil and gas. I'm a big, big believer in thermodynamics. And thermodynamic efficiency really matters. So even in that case, now you look at, well, what do you have to do? So you have a lot of people that say, well, let's just go with no investment. Well, you deplete. Let's just keep the investment in an existing field. Okay, better. But this whole area here is yet to be determined. And the exact same story is true for gas. So I just use the oil side for illustrative purposes. And again, just look at the scale. Just look at these numbers, right? Because on a PowerPoint slide, it just looks like a y-axis. But that is 100 million barrels a day. You all know what a barrel is, right? It's like a big keg, right? You all know what a barrel is, right? 100 million of those every day. And if you look at the right, 1 billion cubic feet, right? 400 billion cubic feet a day. I mean, I'm telling you guys, the scale of this industry just blows my mind because you can't imagine scale. It's like until you see the ocean, you think you see the ocean, then you get on an airplane and you look at the ocean, it's like, wow, that's scale. Scale is the hardest thing to explain. And yet it is the most important thing to understand when you're thinking about energy. It is a scale unlike any other. And so the investment is going to be needed. This is really just an analysis. It's not a defense or an offense, it's just a fact. And the question is, how does this whole energy system integrate together? But it is inclusive. Every form of energy is going to be needed. And what's going to determine what energy you use is geography, economics, all those types of things. But the first step is understanding what your options are. Okay, how do you close this? Well, let's talk about what a transition is. A transition, think about just the word, right? You don't have to be a PhD chemical engineer to understand this. What is a transition? A transition is going from one value chain to another. Because if you stay in the same value chain, you're just optimizing the value chain. And Henry Ford had that very famous line, am I looking for a faster horse or am I looking for a car? The car is a transition, a faster horse is doing what you're doing. But now, is it okay to have a fast horse? Absolutely. Do you want to continue to look for efficiency in what you're doing today? Absolutely. But you also have to be looking at the new value chains. And so this is an IEA report. There's a footnote on the bottom. They put it out each year. I think this was the third year that they published it. And it looks at, I can't remember how many there are, 40 or so value chains. And then just looks at it as an on track. It's happening, but not fast enough. And it's, wow, we're nowhere. It's not on track. And you got to squint, but you'll see a couple of greens. And the greens are basically renewable, solar, primarily solar. EVs, think about that value chain. Was anybody thinking about lithium and cobalt and was critical minerals even a thing 10 years ago? That's an entirely new value chain, right? From the batteries to the type of car to the autonomous driving. Think about all the pieces of that value chain. So that's a new value chain. The purpose is still to drive a car. Just like the purpose of a car versus a horse was just transportation. You all think we're making progress. A tweet is just a telegram, just a lot faster. Uber is hitchhiking. I mean, you know, it's all kinetics. These are all kinetic improvements. And that's really one of the keys to energy. Thermodynamics is not going to change. I don't think. As long as we're on this planet, I think the laws of thermo are going to continue to be the laws of thermo. But what is going to change is kinetics. And so when we do research, we're looking at two things. We're looking at how close are you to thermodynamic limits? Because if you're near the thermodynamic limit, there's probably not a lot of room to improve. And then what's your kinetic arsenal? How many things can you do to change the kinetics? And so that's how we look at, and we're going to get into what we're doing research on in a minute. But if you look at this, that's what this is talking about. These are the value chains that are going to be tweaked. And so we did solar, we did cars, and I think the LED light bulb is the other one. And while that may not sound like a new value chain, it was an entirely new value chain. Because that light bulb had to be totally remade. And it was able to fit into an existing infrastructure, another really important lesson. If you want to accelerate a transition, you try to leverage infrastructure. Right? The EVs didn't need new roads. You could use the same roads. Now, it needed charging stations, but it didn't need new roads. So there's existing infrastructure. The tires are still the tires, things like that. So again, we're looking at ways, how do we actually get technologies deployed? What are the signs that we're looking for that says we can actually go at a speed a little faster? And so as you're thinking of these value chains, break the value chains into the components and understand where we are. That's also, again, in the shape where we need to focus our technology. Because where you see the gap, you're going to work, and I'll get into that in a minute. Sorry, I'm bouncing around a little bit. because I do want to talk about now around progressing solutions. And I want to start with what I call the four prongs of how Exxon looks at this. And they're sort of obvious, so I don't think it'll surprise anybody, but let's just think about this. The first thing is you take care of your own business. And I'll give you examples in a minute, but you reduce methane. You take down your direct emissions. You work on your own operations, right? Take care of your backyard, if you will. Second thing is help out your friends. Provide energy options for customers. Get the LNG out there so it can replace coal. Get the materials out there that can lightweight cars. Get tires out there that can improve air retention. Get lubricants out there that can allow metals to work more efficiently. These are all products we make that we may not deploy ourselves, but they help others. So step one, take care of yourself. Step two, help others. Three, this is what we're doing here. Talk about it. Let's have rational and constructive discussions. Let's agree to disagree. Let's agree to agree. I like to focus on where we agree. Connect the yeses, not connect the nos. Because if you connect the yeses, you'll find that we agree far more than you think. And let's connect the yeses and continue to have this discussion. Why can't we get this out there? What's missing? And then the fourth is previous three slides. This is a technology problem. You cannot policy your way out of this. This is a technology problem, and we don't have an ample technology set. And if the technology, if something is not affordable, that's a technology problem. So find a technology that makes it affordable. If it's not scalable, that's a technology problem. Find a technology that's scalable. If it's not geographically deployable, figure out what can be deployed in that geography. Bring it all back to the science and challenge the scientists. That is what we've done essentially forever. Bring it back to the scientists. Tell them what the problem is. Agree on the problem. We're going to talk about policy in a minute. Get a policy construct that can enable the technology deployment. But remember that until you get to affordable and scalable technologies, they're just not going to deploy. It's as simple as that. How do you do it? So first step is what do you have to do, right? But the what is important. The how becomes critical. And actually, I'm going to pose a way things are done today, and I'm not skilled enough in PowerPoint to be able to turn this into something else, but I'll describe it in a minute. So obviously the way anything works is you discover it, you develop it, you deploy it, and you scale it, okay? That's a linear progress, and if you look at the way the DOE had been doing things, TRL 1, 2, 3, 4, up to 9, that's that linear process. I'll give Evelyn Wang and her team a lot of credit during the last DOE administration, because they said, actually, it's not technical readiness that we need, TRL. It's commercial readiness. And I told her, I said, this is fantastic, because that's actually you want. You want to know when it's ready to deploy commercially, not when it's ready to deploy technically. So let's bring in some of those commercial aspects. But while we're doing that, let's redraw this thing. And instead of doing it in series, because the other thing you learn in physics, you didn't realize it was a physics seminar. The other thing you learn in physics is parallel beats series every day. So how can we do things in parallel? So how can we get the guys that know what they're doing at scale to work with the people that are in the discovery phase? And that's what we're trying to rearrange, right? So that's why we spend so much time at universities. That's why we spend so much time in the ecosystem of development and first deployment, because we're a scale company. We know what our core competency is, right? Our core competency is building big projects and running them reliably. But if you don't have the first three steps, you can never get to the fourth step because you don't start at scale. So now how do we bring our capabilities and bring them back to the front and start having that discussion and start thinking about how do you do this in parallel? Because that's how we're going to get there. And believe it or not, as I interface with universities, it's quite amazing to me when I talk to folks in the lab or even in the ecosystem of the startup funds and that type of thing. And you look at what their process diagram is and what their steps are, and a very simple thing like, that material is not going to scale. or that metal that you're depending on, there's like 5 grams of it in the world. So you might want to rethink how you're designing it up front, which is a lot cheaper than to get all the way to the end, and now you're at the billions of dollars of capital phase to find out that something doesn't work. So rethinking this, I think, is going to be critical to navigating this. And the key word here, and this is why you all are here, is collaboration. Energy is, you don't get a degree in energy. It's always amazed me, right? If you want to be a pharmacist, hopefully you have a degree in pharmacy. A chemist is going to have a degree in chemistry. But you want to enter the energy industry. What do you get a degree in? We need it all. In my view, it's a pretty bold statement, but I'll make it anyway. It is the only industry that requires every discipline of science, every discipline of engineering, every discipline of social science, economics, everything, all coming together to do what we showed you in the earlier charts, to get to that scale that we are today. So how we collaborate, how we redesign curricula in colleges around this energy challenge, I think is going to be really, really important, because I think this is the problem. And collaboration and research and all those types of things are going to really be the enablers. Okay, last sort of theoretical thing, and then we're going to get into practicality, and that is, well, what is a piece of this successful transition? So I already talked about policy and technology working together. Policy has to have line of sight to a market, because you can't policy forever. And technology has to have line of sight to scale. So you need markets and scale, but if you bring it down to its first step, it's policy and technology. So how do you get policy and technology working together? You really don't want to pick winners and losers. You want to keep it as technology agnostic as you can, recognizing that that's really hard to do, but you want it to be technology agnostic. But you want policy and technology to work together. You got to remember that the world needs more energy. So you don't want policies, and many of the policies today, when you actually do the math and you actually play it all out, it actually reduces supply. And one of the things that confuses everyone is what I'm talking about on the bottom, which has been sort of my area of focus for the better part of 10 years, is on this: how do you actually track emissions? So call it accounting. How do you actually account for emissions? And the fact of the matter is we don't have an accounting system today. And so actually today, there was an announcement made this morning of a cross-industry collaboration to advance carbon accounting. It's called Carbon Measures. So if you go to carbonmeasures.org, hopefully the website's still working, because I heard there were some issues this morning, but I'm sure they've got that fixed. But it really talks about the principles of accounting. And it, again, talk about collaboration. It talks about bringing two things together. It talks about bringing the fundamentals, or the accounting professors are getting out of me, the principles of accounting, of which there's only 3 or 4. You count everything that's material, you count it only once, and you allocate it to products. Those are the principles of financial accounting. That's how we run the world today. And then bring in chemical engineering, which is a defined system boundary. It's got a material balance. And you bring those things together, now you've got a system. And that's what Carbon Measure is going to try to do. So it's an accounting framework with product level carbon intensity, so that on one ledger, on one piece of paper, you know what the emissions are of that boundary, and you know the emissions intensity of every product that's leaving that boundary. And it goes from boundary to boundary to boundary. There's no double counting now, because you leave that with a ticket, or a token, I guess is the word they use. And then that token goes to the next step, and the next step, and the next step. And by the time you're done, guess what? It's going to material balance. So the concept of a chemical engineer was like ridiculously simple, but bringing the accounting framework, which I'm not, but I've actually been working with some folks from Harvard and Oxford on these accounting principles, is what this is. And so the other piece of the puzzle here is getting, again, energy is so complicated. So getting cross-industry collaboration. That's what that Carbon Measures thing is. It's around 20 companies. I don't know the exact count that's published today, but around 20 companies cross industry, cross geographies, saying, well, let's really work on this. What would this look like? Because if you look at the graphics on the right, this was, I think, a Science article that said there's been around 1,500 climate policies, and only 63 of them have actually demonstrated a reduction in emissions. It's probably not a very good batting average. And on the lower right is what we think is needed. You need to know the CO2 per X, imagine everything has a label on it, just like your food does today. And you know what the CO2 per ton of steel is. So you all have probably heard about Europe, CBAM, and some of the other border things. Well, they only work if you know what the CO2 per product was as it crosses the border. You do that, you have the accounting framework that underpins it so that everybody's doing the math the same way, which is how our financial system works today, whether it's US GAAP or IFRS, the commonality, so I can look at a balance sheet from a Chinese company or a balance sheet from a US company, and to a first approximation, I can, what's the word they use in accounting? It's comparable, because they're on the same basis. We don't have that today. We have an accounting system that's not really accounting. It's a reporting system. It's a disclosure system. And it's important to understand the distinction between accounting and accountability, reporting and disclosing, and scenarios and target setting. These are not synonyms, but they are used as synonyms today. And that, I think, is causing some confusion. So the beauty, the fun part about coming here is we get to have a discussion and say, well, let's just agree on definitions. Because I think if we can get agreement on definitions, and I think there is a finite definition for all those words I just gave, then I think we're well on our way to an accounting system that can allow action to be taken. And at the end of the day, what you're really trying to do is drive competition. So if you have the lowest carbon intensity product, you should be rewarded. Only if you can compare your product with somebody else's. Only if you can compare your grid with somebody else's grid, and that everything is accounted for. So you can't randomly select what electron you're taking. You're taking the electron as it was produced when you used it. It's really quite simple if you think about it. Now, the complexity of getting to 650 exajoules of energy and all the other stuff is hard, but that's a computational issue. That's not a conceptual issue. And I do think that AI and all the advances we have in computing is actually going to make what I just described a lot easier. And it'll also allow you to, I'll tell you one of the questions, well, what do you know? You don't know the emissions associated with that step. You know the chemistry. So at a minimum, just start with stoichiometry. What is going to enable this? Money, right? So financial accounting is great, but as you know, money's a concept. Money's not actually a measurable thing. Money's a concept. The thing about climate is CO2 is not a concept. CO2 is real. And we know what the ultimate material balance is. It's 57 gigatons. Or 423 ppm, whatever you want to pick. And if you want to limit it to just energy, it's 37 gigatons. But the point is we know the macro balance. And so we know if we're moving in the right direction. Are we going to add up to 37 step one? Probably not. But that's introducing another accounting term that I've learned recently. But you do it through recursion. Each time around the loop, you get a little better. And where you didn't know what the answer was and you had a placeholder, okay, well, we'll get it fixed the next time. And you get it fixed the next time. And if you look at what we've done with accounting since 1935, I just screwed up one of my great questions. You do know when, now you know, but US GAAP was 1935. It's less than 100 years old. Accounting goes back to the beginning of time, right? In fact, when they found the original ledgers as they were digging through the pyramids and everything, people thought, oh my goodness, let's see what these guys were writing about. They were probably talking about the sun and the moon. And no, actually, when you looked at it, it was like Fred owes Joe $4. So accounting goes back all the way to the beginning of time. So we're not changing accounting. We're trying to bring in the thermodynamics of accounting so that we can actually get this to work. And that's what this is about. I'm spending a little bit more time on this because this is the first time I'm ever using this slide, because today is the day we announced the coalition, so I wasn't allowed to use this slide until today, but I'm excited to use this slide. I think this is going to be one of the great enablers. A Harvard professor, Bob Kaplan, and an Oxford professor who was a Harvard professor before he went to Oxford, Karthik Ramanan, are the pioneers in this space. I'd encourage you to read their work. It's under E. Ledger's Institute, which is worth reading, and now Carbon Measures, which is an industry-led thing, which is going to focus on ledger-based accounting, is going to try to bring this and reduce it to practice. So this is super exciting. I think this could be one of the game-changing moments in this space. And you were in the room when the announcement was made. So there you go. And now finally at the last section, I do want to talk about Exxon a little bit, because I think the best way to present something and show an example is talk about yourself. So I'm not going to talk about anybody else's strategy. I'm not going to talk about anything else. I am going to tell you what we're doing, because this is all factually correct. It's so factually correct that if you look at the footnote, this is all out of the stuff we report to Wall Street. So it's out of our earnings reports and out of our investment communications. And you know those things are very, very much regulated. So the left-hand side is what we're doing to grow energy, because the world needs more energy. And look at the numbers there. They're super. 4.3 million barrels a day, right? Highest liquid production. Proxima is a new carbon material. And then upstream production growth. Big, big numbers. On the right is what we're trying to do to lower emissions. So focusing on methane, allocating capital to lower emission investments. I mean, $30 billion. Biofuels or low emission fuels. Now notice the units, 20,000 barrels. 4.3 million, 20,000. But that's exactly the origin of transition. Transitions always start small scale and work their way up. And so that's where we are right now. It's not surprising that the right is far lower than the left. The left's had a 130-year head start. The right's just getting off the block. You don't want the left to slow down. When you're running a relay race, you don't tell the guy that's running the first 100 meters, slow down the last 10. Okay, because no, you want that guy to run through the wall. And the other guy, you're saying, it's going to take you the first 20 meters to get up to speed. But how do you win a transition? How do you win a relay? You win it in the transition. The transition is the critical part of winning a relay race. And so this is how we're looking at the transition. Keep running hard and start running. And eventually they'll flip. But we don't know that pace, so we got to be ready to go as the market evolves, as the technology evolves, as society evolves. We've got to be ready. And so you need to have strong portfolios in both. And I was fortunate enough to lead the R&D group for about 10 years, and I can tell you that we continue to build our portfolios here. And we continue to work on how to accelerate the deployment through the innovation pipeline that I talked about. And then finally, what do you need to do? So that's the what, this is the how. And so what are your degrees of freedom or your tools, whatever you want to call it, right? So we talk about working towards the ambitions in 2050. Well, the first, equipment upgrades is really important, as is electrification. So if you can do your work, remember, work is energy. If you can do your work with an electron, do it with an electron. Now, it is critically important where that electron comes from, but use the electron. We're doing that in the Permian. We're doing that in our base operations, right, where we can electrify. That's one of the best ways to reduce methane, is to replace pneumatic valves with electric pumps. And then you're not burping out the methane, right? It's just running smoothly in electric. So electrification, equipment, technology, renewable power agreements, policy, and then having, instead of a 2050 plan, break it into pieces. By 2030, I want to be here. By 2035, I want to be here. And you work your way up. And then you're ready to accelerate when you see the technology come through. You guys, I see a lot of nodding, because this is really not that complicated. It's pretty much common sense. The great uncertainty is technology. One thing you cannot predict is I used to love it when people would tell me, we'll invent it in the next 5. You can't time an invention. What you can do is what I talked about earlier, is change the way we're innovating. Encourage the collaboration, encourage these types of discussions, get the research going. It's a technology race. And, I'd like to win that technology race. So finally, we'll get to questions then. It's really important, that first bullet. I know there's a lot of people that challenge me when I say that, but hopefully I showed you, we don't have the technology. We have the concepts, but we haven't reduced them to scale. And there's a big difference between having a concept. I play golf, and every Sunday I stand on that first tee and I say, I am going to shoot a 75, because I get it. And then when I reduce it to practice, I end up shooting an 85 and I go back to the drawing board, right? So we don't have the technology. That doesn't mean we can't have the technology. It just means the current technology doesn't meet the needs. We know how to do technology. I didn't get into the history of Exxon, but we've been around a long time. We deployed the first petrochemical isopropyl alcohol. We deployed the first fluid catalytic cracker, which produced the aviation fuels during World War II. We invented synthetic rubber. One of our scientists just got the Nobel Prize for the lithium-ion battery. We've been on the foreground of deep water exploration, of digital seismic interpretation. So we know how to scale. And we build capabilities around scaling technologies. And so we build our capabilities, we continue to build those capabilities. We know how to do it. And it's because we're, as our chairman will say a lot, we're a technology company. Now, what is technology? Technology is science meets engineering. So you can be a science company, you can be an engineering company, but if you want to be a technology company, it's that intersection of science and engineering. It's understanding the basics and the reduction of practice. So science and engineering. And then finally, we talked about it. It is going to be that triangle. You need policy, you need technology. But I softly mentioned the third leg of that triangle, but it's a critical third leg, and that's infrastructure. And now make this a kinetics problem. Every one of these technologies, every idea, whenever I go visit a startup, and I've been lucky enough to be on advisory panels and all sorts of fun stuff over my career, I always tell them to draw out their flow chain, their value chain, and tell me what the limit is. It's going to be one of the three. It's either going to be, I don't have a technology, don't have a policy, or increasingly, don't have the infrastructure. And I include permits and infrastructure. So if you look at one of the real rate limiting steps today that is underappreciated, it is permitting. And so once you know, this becomes a kinetics problem, once you know what your rate limiting step is, fix it, and then move to the next rate limiting step. Fix it, move to the next rate. This is an infinite loop. You'll never be done. Go back to my concept of infinity. There's always improvement, but you will asymptote. And that's the other concept from economics, which is the experience curve does level off. Right? You don't keep getting faster as you work out, you level off. But understanding that curve and where you on that curve is going to help you place not just your investment bets, but also where you want to put your technology focus, et cetera. So that's it. I just wanted to take you around how we think about it, bring in some elements that maybe you hadn't thought about, and really encourage you because, one, I think it's awesome that we have so many people here. It shows the interest in this topic, which is really great. These are the best minds in the world that I'm looking at. You are not looking at the best mind in the world. I'm looking at the best. Right? This is not a mirror. Okay, what I see is not what you see. You see a guy who's been around a real long time. If you'd have told me in 1987 we'd be doing energy the way we're doing it today, no way. Not a chance. I'd have gotten a 0 on that exam. So if I give you a blank sheet of paper today, you're going to be behind this podium in 35 years. Okay? What's the technology mix going to look like? Don't limit your imagination. Don't limit your imagination. Energy is going to enable people to prosper. Energy is going to close the wealth gap that I showed you on that previous page. Energy is a great equalizer. Emissions are a challenge. We got to bring energy and emissions together. That's going to change your priority of which technologies to pursue. Bring it all together, have an accounting system that allows you to recognize the emissions options for the various technologies, which we don't have today. Put it all together. Fast forward 35 years, and I'm kind of liking our chances, but we just have to work together. Okay? I'm open to questions if you guys have any. Thanks.
Let me start with the first question before we go.
Really,
to the
you?
audience. Yes.
Moderator's
prerogative.
prerogatives? Okay.
Yes. So I want to return to this theme of scale and the importance of scale, and some of what you worked on when leading the R&D division focused on those technologies on the right, on biofuels, on hydrogen, on CCS and direct air capture. They're all relatively small scale today. You need to have the kind of further innovation to drive down the costs, but we know from other technologies, the policy environment matters for helping to sort of build out the market and in facilitating or enabling scale. Certainly that's been a story we've seen for solar, where policy helped build out, and we saw the tremendous cost reductions for solar. So when you're thinking about how scale could enable that transition, get that second runner in the relay race to get going a little bit faster, you've now got this new foundation potentially of how we measure emissions. What do you think of as like this, say, policies for the next 5 or 10 years? Maybe there are policies already on the books in some places and not others, but what policies do you think would really help enable the sort of scaling of these next generation technologies faster?
So I'm going to work that backwards because I'm going to start as an engineer and say, actually, we understand scale pretty well in engineering. And drawing a blank on her name. She's a University of Pennsylvania professor. She was the Assistant Secretary of Energy. And I'm drawing a blank on her name. But anyway, if you think about engineering energy processes, they scale, generally speaking, they scale one of two ways. They either scale by numbering up, meaning you make one and then you just make a whole bunch of them, like a battery, like a solar panel, something like that. Or they size up, which is what a steam cracker or a catalytic cracker or something like that does, right? So you build one and then you make it bigger the next time and you make it bigger the next time. So number up or size up. And they have different curves. Numbering up is lower capital because you can do it with just a few numbers and it goes faster. So it's how long does it take you to double capacity, right? So if you number up, which is what solar panels did, which is what batteries are doing, you can number up, you can come down a cost curve faster. Size up, which is what steam cracking, things like that, right? Takes longer, is more capital, but you get to scale faster. So going back again to when you're in the startup community and you're talking to various companies, understanding what their value chain is, what their technology pathway is, and then understanding for each one of the components. I talked about rate limiting steps before. Now I'm going to talk about, is that step a number or a scale? So the material, the catalyst could be a number. The reactor is probably a size. And breaking it down into those chemical engineering blocks and understanding which one you know, which one you don't know is going to shape where you want to focus your research, which is what we try to do in R&D. Because energy is really pretty simple. I talked about, find it, convert it, use it. But if you look at the three things that underpin it, it's materials, catalysts, metallurgy, right? It's materials, it's process configurations, how do you design the process, and it's computing. Those are the three core capabilities. So you have the three core capabilities, you have the three, you bring all these rate limiting steps together, and now you can sort of build the pathway. And that's what we try to do when we do research. We understand where we are today, all these other components, and then how do we either collaborate with somebody that has a skill we don't have, or develop ourselves. The policy construct now comes back to the economics, which is, where are you? You guys know what a cost curve is, right? So if the y-axis is dollars per ton and the x-axis is scale, you want to know where this particular technology sits on a cost curve. But more equally important is imagine a CO2 curve. Because the cost curve is a one-dimensional problem, right? I just need to be lower cost. I already told you that's not the problem. The problem is lower cost and lower emissions. So you need to know where you sit on the CO2 per ton curve as well. And now if you can bring the cost curve and the CO2 per ton curve together, now you can start having a policy that says, how do I get the thing that's outside on the cost, but inside on the CO2? How do I flip it? And now you bring in all the economics theories around affordability and all those other things. But now I like turning things into an algorithm. Now we're being algorithmic about this. There's no emotion. This is all data, all facts, and now pragmatic steps that we can take to continue to have reliable energy while we start the process of lowering emissions. That close?
No, I'd like to hear more. Like, so what is that policy?
That means I didn't answer the question, right?
You've given me a little bit of like,
well,
here's how I as a scientist think about it.
I don't think
you also engage on policy at Exxon.
Well, I think the policy, you know, you look at the IRA. The IRA had a lot of these components. If you look at the hydrogen policy, it didn't talk about colors. It talked about grams of CO2 per ton of hydrogen. That's a technology agnostic policy. We like technology agnostic policies. You want all technologies to compete. EV policies pick the technology. By definition, right? It's an EV, it's right there in the word, right? So what you want to do is you want to pick policies that are agnostic to technology. And the more you can do that, the more shots you'll have at solving it.
Okay, so there are these policies that have promoted technologies.
Yep.
You noted, I mean, there's one way to think about hydrogen. You could say it was just looking at the emissions profile, so it's technology neutral, but it's again in a very narrow space, the hydrogen space. Right? But so like there are clean energy subsidies you like. When you think about what we need to do to achieve some of these goals, and Exxon has its own goal to get to net zero by 2050, are the subsidies going to be sufficient, or do you see other policies, perhaps some kind of performance standard that I think is potentially implicit on this kind of carbon measure strategy? Do you see that down the line as something that could help?
Yeah, I think if you can move to a product intensity standard, we just did this. You guys know that we just did this in IMO, International Marine Oil, Marine Fuel. Took the sulfur specification from, I think, 3.5% to 500 ppm. And we did that through technology development. And we also did that through, if you're lower than the spec, you're valued because you can blend to help somebody else, right? So you're really looking for a policy construct that rewards technology innovation and rewards over performance. Again, that's very common sense. But in CO2, in order to do that, you have to have a level accounting system. So that when we calculate the CO2 per ton of hydrogen, it's the same way that another company. Or when ERCOT is calculating CO2 per watt, it's the same way that the Chinese grid is calculating CO2 per watt. So a critical enabler for CO2, because the problem with CO2 is we all know that a lot of CO2 went into making this aluminum can. But you can't take a sample of this aluminum can and measure it. So you need the underlying accounting as to how this went from the ore to the aluminum, to the smelter, to the fabricator, to finally this can. Each one of those steps had a CO2 piece. And you want to drive competition in each one of those steps. Because if I'm the can maker, I'm going to look upstream and say, I want to find a producer that can have lower CO2 per ton than my other guy. And so that's what we call policy forming a market, because through the transparency of CO2 per ton, you force people to say, well, I want something. You see elements of that today, but without a common accounting system. And I think the common accounting system is going to unlock a lot of this, particularly if we can do it internationally. And that carbon measures thing, not to make another plug for it, but that carbon measures thing is an international collaboration of companies.
Okay, so let me open it up to questions from the audience.
Thanks for the presentation. If we focus on Exxon alone, what is something that you wish Exxon's doing in the climate space that it's not?
I'm pretty pleased with, I'm biased, okay? Having had the job for the last 3 years, but I'm never satisfied. I think there's again, go back to my concept of infinity. I think we do more of this. Again, thank you to the team for inviting me out here. I think we can always work on collaborating more, on looking for technologies. I think we should always look for faster ways to deploy. By the way, this is nothing different than what management tells us all the time, right? So I think you should never be satisfied. But I think, being overly critical is also not very good. So I think you need to look at what you're doing, analyze yourself, look for where you can improve. And again, I don't think you can improve in all spaces simultaneously. So maybe we can improve by doing carbon measures. Maybe we can improve by having more of these discussions. Our chairman's gone to the last few COPs to drive the discussion. We joined OGMP, we did OGDC. So we're trying to drive the discussion. We're trying to tell you what we're doing, listen to hey, we think you can do this better. We think you can do that better. Okay, well, let's listen. But I think it's that continuous improvement loop. And I think, the pressure that I try to put on people, and hopefully my successors do, is just to never be happy. Always keep looking to get better.
Hi, thank you for the conversation today. I had a question about how you actually enforce or kind of highlight the priority of clean energy. I used to work in the private sector on sustainable research, and I saw as the political landscape shifted, like basically the work I was doing was no longer prioritized. And so how do you cut through that political noise and actually make sure people are listening to what you're saying? And you're not just kind of reactive.
So a lot of when I get to interact with universities, a lot of the questions I get end up becoming leadership questions more than an energy question or anything like that. We've been around a long time. We've seen administrations come, administrations go. Energy is super complicated. You can't snap around when you're making capital decisions like we're making. Projects take 5 years to build. And so what you want is certainty, what you want is clarity, but you also know what you're good at. And you have to have the confidence when you build a project that it's going to work when times are good and it's going to work when times are bad. This is a cyclical business at the end of the day. And so when we're doing a project, we are testing it against all of those scenarios, which is why we say that you can't solely rely on policy. We invest. It's going to run 50 years, 100 years. You come to Baton Rouge, you come to Baytown, you come to some of our places. They've been around a long, long time. And so do you really know what's going to be in 50 years? No, but you do know that if you have competitive technology, advantage technology, if you know how to operate reliably, then you should be pretty good over the totality of time. Are there going to be ebbs and flows? Of course. But for a company our size, of our scale, you keep your head down, and you know that at the end of the day, the product you're making is not wanted, it's needed. As I showed, energy is needed and more energy is going to be needed. So you ground yourself in that fact, and now you say, I'm going to apply, our capabilities so that where we think we're going to compete under a variety of scenarios, policy, technology disruption, whatever. And you're never done with the types of scenarios because the last 5 years we've lived through a series of who'd have ever thoughts. But you've got to have that resiliency built into your investment profile.
Thank you, Vijay, for your presentation. My question is, I think, similar, but from a different perspective, from the perspective of capital allocation. So from what I know, on the left side of your presentation, Exxon is printing money, like it's going really well for that side. So from the company's perspective, how to decide how much money allocate into the right side of your chart, like this new energy side? especially since it seems like it's like a chicken and an egg thing, right? So you put more money and maybe it's going to create more demand, but you don't know, and you have this left side or traditional business where you are actually seeing results of that money. How is ExxonMobil thinking about it, and how is kind of like the research side of things influencing on that perspective? Thank you.
Yeah, I mean, it's a great question. The answer is pretty simple, and it's you all know how to manage a portfolio, and it's portfolio management. So, our management team looks at capital allocation. Our board looks at capital allocation because it's choices of what do you do with your capital. And, and then it's the best use of your capital. So it's shareholder return, it's long-term return, it's all those various concepts. It's, I need to get that first deployment out there because I know if I get that first deployment, the second, the third, or fourth will be better. And so we need to allocate the capital to that. That comes back to, well, how do I minimize the capital for that particular first plant? So that when we're deploying a technology, we're in, you see all the stuff we're into in the carbon capture and in the hydrogen and those things. All of those things, because you want to get the most use out of your capital. And, our shareholders expect us to take care of their capital because that's whose capital it is, right? We worked for shareholders. And so you want to take that capital and you want to allocate it in the best way, and you need to have the right rationale. But it's no different than all of you probably have an E-Trade account or have some sort of a portfolio thing. And so why don't you bet it all on one stock? You could, but you don't, because you have to understand how to manage portfolio. And that's what the people in the really big offices in our company, that's what they spend their time on. What's the best capital allocation? Our job at the more working level is to really explain why we think this is a make sense project or why we think this research is worth pursuing. But then ultimately you have to have a decision maker, and for us it's our chairman and our board, and they will make those decisions on the capital allocation.
Thank you so much for being here. And building on that last question, I wanted to ask you, so when it comes to these efforts you describe on reducing emissions, in the presentation you talked about how these efforts are kind of just getting off the block. And I'm curious, I'm sure you get this question all the time, but I'm really curious in hearing your particular perspective on why there has been this delay, given that Exxon researchers, of course, were looking into this in the late 70s and 80s.
So let's make sure we understand. Pronouns are a real problem, right? So let's make sure we define this. So Exxon has been doing research going back to the origins of Exxon, right? Like I told you, we were the first to do chemicals, things like that. We're always looking for ways to improve what we're doing today and responding to the market and responding to the policy and responding to things like that. So why is it taking so long to get off the ground? Well, let's take carbon capture, for instance, because we've been doing carbon capture longer than anyone else. That's a fact. And why hasn't it hit the scales that we want to hit it yet? In my opinion, we don't have the right material yet. We're still using a liquid amine and a kind of a liquid-liquid or a gas-liquid extraction, where you push the gas through the liquid, the droplets pick up the CO2, and then you go through a thing. I think we're going to move to a solid material. And if you actually look at the research that we've been doing, it's been on these solid materials. The Nobel Prize for chemistry went to a professor who was on the pioneering front of metal organic frameworks, a whole new class of materials, totally game-changing. I'm a huge, huge fan of MOFs, but no one has really scaled them off yet. So you can't put a timing on research. We were working on the lithium-ion battery, of which I'm really bad at names today. Stan Whittingham got the Nobel Prize for the lithium-ion battery. That research was done in the 70s. So let's make sure we're having this is you have to keep doing research, but you have to get that research that can go back to my earlier chart that has to be ready for scale. And what you're beginning to see now is, the solar panel goes back to the 50s, the 40s. It accelerated a little during NASA. But until, the DOE and ARPA-E came up with a way to fabricate that panel, the triple junction nodes, to be able to get the efficiency where we needed to, that was the breakthrough. So the research is continuous. You're absolutely right. We've been doing research for a long, long time. And then it's just a question of when is it ready to take out and deploy. And I'm hoping that our pipeline is pretty strong, and as the technologies get ready, they deploy.
Thank you for the presentation. This is perhaps building a little bit on Professor Aldi's question, but just when earlier you say that successful policies should avoid picking winners, I'm thinking a little bit of things like shipping fuels, and where I understand the lack of kind of consensus and the best shipping fuels kind of holding back decarbonization, but more generally kind of companies understanding where their energy sit on the cost curve. What's your thinking on how to find a market for renewables when the market hasn't really been able to maybe drive them forward to the extent that's necessary now without more proactive policies?
So I'm going to go back to plugging the coalition again, carbon measures, because my hypothesis is if you had a intensity specification that you have to meet, you would drive competition to meet it. So renewables are great. Renewables are not zero, as you know, because there's a lot of CO2 that goes into making the solar panel. You still have the transmission, you still have all those other things. But it's an all of the above challenge. And the more we're able to compare one pathway to another on an apples to apples. Okay, this is the big debate on the EV versus the ICE. Really, it comes down to your grid. If you've got a coal-based grid, I would tell you that the EV is probably not the lowest emission vehicle. But it's connecting all those dots. So it's, again, it goes back to what I said earlier. Build your pathway. Understand each step of the pathway. And if it turns out that what's really limiting you from having the lowest carbon intensity is the grid, well, fix the grid. If the grid can't be fixed because you're missing a material to do carbon capture because you want to do a coal-based grid or a gas-based grid, fix the material. But keep coming back to what's the next thing we need to work on so that we can keep, you really want to think of it an X plus delta X problem, and you want delta X to be better than X. So the next step should be better than the previous step, and keep driving our choices in that direction. And then a policy construct can help close the gap, but it can't be there forever. So the policy has to understand how the costs are going to come down so that the policy can ultimately go away and then the market just takes over. So policy, line of sight to market, technology, line of sight to scale. And if you can bring those two together, then you can start making informed decisions.
All right, thank you so much. Really interesting talk. I was just curious to jump back to that graph you showed about projections for global oil demand through 2050. And I thought it's worth noting that Exxon's projections seem to show like relatively flat consumption through 2050, which differs quite a bit from what some other folks in the space are saying, not just like baseline IEA scenarios, but also what peers like BP are saying, who see a peak in global demand sometime in the 2030s, maybe. And obviously that's fair game. Different modelers come with different assumptions. These are, arts as much as they are sciences. But I was just curious if you could talk about some of the assumptions going into the graph you shared and like why Exxon sees, 2050 playing out very differently than some peers in the fossil fuel industry.
You guys are so smart. The answers are in your questions. So I listen to your questions. I'm like, I just got to rephrase the question in the form of an answer. So we, as I said, we have a team of economists who do their best. I'm not on the team, but I'm on sort of external to the team. And it's what they actually go visit the countries. They'll go. In fact, they go on a world tour. I think they're going to India in a couple of weeks. They go to China. They go spend a lot of time in the U.S. really trying to understand what is happening. What are the supply-demand fundamentals? We read as much as we can read. The IEA reports are really good, but it's modeling at the end of it, like you said. And the point of that chart is just to show you that range. I mean, the one spaghetti chart I showed you with all of the scenarios that the IPCC puts out, that's an incredible range. And so you guys know the quote, right? All models are wrong, some are useful. When we put our outlook out, and I give our management a lot of credit here, we're putting out there what we think is going to happen, not a scenario. Or we don't call it a scenario. We call it an outlook. There's a big difference between a scenario and an outlook. An outlook is what you see. A scenario is, there's a bunch of chances. And so I think the fact that that's to me the distinction between what we do and what others do. We don't give you 500, we don't give you a bunch of scenarios. We're giving you an outlook, and let's have the discussion. All we know, and in fact, in this year's outlook, we actually went back 10 years and said, well, what did we say 10 years ago? And how far off were we? Some things we were pretty good and some things we weren't so good. But that's the continuous improvement group thing that group tries to do. So there is no answer to your question, like you said. I think the answer to your question is what we're doing here. Let's show what we're doing. And if we have other ideas, let's incorporate those ideas. Because again, I really do think we are all trying to solve to the same problem. And I have to believe it because I'm a sort of a optimist. I think we're all trying to solve the more energy, lower emissions problem. I don't think we're trying to pick winners and losers. I don't think we're trying to bias the playing field. I think the vast majority of people really just want power. They really just want airplanes. They want power. They want their computers. They want their internet. That's what they want. And they're leaving the rest to us. It's a huge responsibility. And that's why you guys are here, right? That's what makes Harvard Harvard. You are thinking at that dimension. And thank heavens you are. Because you're thinking at that because you're thinking in that dimensional space, the others don't. So Harvard has a capability unlike any other. And this whole ecosystem here, Harvard, MIT, Tufts, et cetera, right? This is a ridiculous ecosystem. We're talking about the intensity spec here, but that's what's needed. And I think if we do our job in driving forward solutions, driving forward policy solutions, technology solutions, infrastructure solutions, bringing it all together, I will tell you, the rest of the world is really hoping for us. Because if we do our jobs, this is going to take care of itself. Every time I come to a university, and I should have started by thanking you all, the optimism in universities is awesome. You're always the same age. Every time I come here, I'm a year older. I've been doing this a real long time, and I keep getting older, and you all keep looking younger. And then I realized it's the delta. And so I used to benchmark you. Well, you guys are, my kids are in junior high school or high school. Then it was, oh, my kids are in college, so I can kind of see my kids in you. Now my kids are out of college. One's in his 5th year of grad school. And I'm looking and I was like, oh boy, this is not ending well. But it is students and faculty and this ecosystem that you please take advantage of it. You don't realize how special what you have is because it's normal, right? Because it's normal and it's not. So please, I ask you, since you guys asked me a bunch of questions, I now ask you, take advantage of what you have. Challenge constructively. They'll give you my contact information. Reach out, ask the question. I'll do my best to answer it. If I can't answer it, I'll tell him to answer it. But we'll figure out how to answer it. If we, again, last theme, collaboration. This isn't all of the above. It's an us problem. And the more we can make it an us problem and not a you problem, we got a better chance of solving it. Thank you for your time.
Thank you, Vijay. That's fantastic. So before we wrap up, I'll just note we'll meet again in a week. Heather Boucher will be here for her talk, Building a Clean, Equitable Energy Future. Where do we go from here? Vijay, thank you so much for your perspective and your insights today.